Okay, g'day all and welcome to another video. So the topic of today is how do spell checkers work? And in particular, what we're going to be looking at is a very famous and very useful algorithm, the Levenshtein Edit Distance. Okay, so before we get into the video today, I just want to point out what spell checkers do. So what a spell checker does is it looks at a word and it determines if it's in a preset dictionary. And if the word is in the dictionary, then it doesn't do anything. And if the word's not in the dictionary of allowed words, it actually figures out the closest words from its dictionary that you might have meant. And from that, it offers suggestions, say the top 5. But the interesting part, and the part that's going to form the main body of this video today, is how. How do they know how close a word is to another word in the dictionary? Okay, so the idea that Levenshtein Edit Distance actually solves is it gives us a metric or a number that we can use to determine the difference between two strings. So the metric that the algorithm computes is called the edit distance. And what it reflects is the number of edits that a user would need to make to one word in order to change it into another. The 3 types of edit that the original Levenshtein allows is insertion. We can insert a new character at any point in our string. We can substitute one character for another. And the other thing that we can do is delete or remove a character from the string. And those are the only 3 things that we're allowed to do. There are other versions of Levenshtein. I think it's called the Damerau Levenshtein, which also allows switching to adjacent characters. But we're just looking at the basic Levenshtein today. For example, if we wanted to turn the word truck into the word struck, then we could just insert an S at the beginning. So that would be the insertion operator. If we wanted to turn the word truck into the word track, then we could substitute the U for an A. That would be the substitution operation. And then the other one that we could do, if we wanted to turn the word truck into the word ruck, like a rucksack, just delete the T from the start. So that would be an example of the deletion operation. So that seems fairly trivial. I mean, to turn the word, say, truck into track, there's only one letter that's different. Things do get a lot more interesting. What about the edit distance between something like the word dinosaur and paragraph? So if you were only using insertion, substitution, and deletion, and you wanted to turn the word dinosaur into the word paragraph using as few operations as possible, it's not at all clear how you would go about figuring out the operations or even how many operations are required to turn dinosaur into paragraph. Okay, so here is the original Levenshtein edit distance. This is how Mr. Wagner Levenshtein wrote out his algorithm himself. We're going to go through a bunch of different versions of this, but this first one I think is interesting because this is kind of where it all came from. It was actually defined as a recursive piecewise function. The Lev, or the Levenshtein edit distance between two strings A and B, is defined as follows. These bars around the A just here, they mean the length of the string A. This top line just here says that the Levenshtein edit distance between strings A and B is the length of string A if string B is empty. And the reverse is true too. So if the A string is empty, if the length of the string A is empty and the B string has something in it, then the result of Levenshtein will be the length of the string B. The next line is really quite interesting. I think this is one of the key insights that Mr. Wagner Levenshtein made. If the strings A and B start with the same character, I don't know, dinosaur and dog, both start with D, then you don't have to edit that first character. So the Levenshtein edit distance between dog and dinosaur would be the same as the Levenshtein edit distance without that first character. So that's what this line just here is saying. The final section just here specifies the operations themselves, insertion, substitution, and deletion. Whatever is the smallest is what we take. So the minimum plus 1. What you'll notice is that we just remove a character from A and we check the Levenshtein distance. Then we remove a character from B and we check the Levenshtein edit distance. Then we remove a character from both of them and check the substitution, again checking the Levenshtein edit distance, and whichever is the smallest out of those 3 operations, we just add 1 to that. So what you can see is that Levenshtein edit distance is really brute force, recursively checking every possible way that we could edit these strings. And that's really kind of where this initial version falls apart. So It's recursive, and it actually checks the same strings over and over again, repeatedly computing the Levenshtein edit distance on the same strings. It's actually really, really slow. This right here is code. I've just couted or printed to the screen the strings that this particular call to Levenshtein is actually comparing. So we're going to be comparing the words cabbages and rabbits using the original recursive Levenshtein function. It's actually going to output to the screen all of the comparisons that it's making. Would you look at that? There's just thousands of them. Comparing S and T, comparing GES and T. These are all of the recursive calls. Yeah, comparing the different bits of the strings. But what you'll see is the same thing over and over again. So for example, just here, it's comparing ES and T. And just here, it's computing the Levenshtein edit distance between ES and T again. So when you use the recursive original version of Levenshtein, it actually ends up being very, very slow. It'll give you the right answer, but it's very, very slow. So that is where the Wagner Fischer algorithm comes in. So Wagner Fischer algorithm is named after its inventors, presumably Wagner, who was a keen fisherman. It might actually be Wagner. Okay, so what we want to do really is look at different approaches to computing the same Levenshtein edit distance, but we don't want to do the original recursive function because it's just too slow. It keeps computing the same edit distances over and over again. The idea with this version is to use a matrix or just a 2D array, and to record the edit distances as we compute them. And that way we can avoid recomputing the same edit distances over and over again. This should, in theory and in practice, speed things up vastly. The first thing that we do is we allocate a two-dimensional array, 2D, 2 dimensions, and the dimensions of this array along the X is cabbages plus 1, or the length of your first word plus 1, and the height is the length of your other word, or rabbit, plus 1. Our array just here is going to be 9 by 7. Our objective is to fill up all of the elements of this matrix, and our Levenshtein edit distance score, our final score, will be in the lower right-hand corner. So the reason that we allocate an extra row and column is actually because the first row and column corresponds to the empty string, or a string with nothing in it. These letters are not actually stored in the matrix, but I'll just put them up there just because it makes things a little bit easier to read. Okay, now the idea is that we're going to fill up each of the elements of this matrix. The numbers that we're going to put in the boxes are the corresponding substring edit distances. So this box just here corresponds to CAB, you see, because it kind of is in line with the B up there in terms of columns. And it also corresponds to RA. Cab and Ra are two sort of substrings. And this box just here is actually going to store a number that corresponds to the edit distance between those substrings. This first row just here corresponds to how many edits would be required to transform some string, some substring of the word cabbages into the empty string. And it's just integers, because if you think about it, if you wanted to transform the substring C into the empty string, you would just delete the C. That's one edit. If you wanted to transform the word, say, cab into the empty string, then you would just delete the C, then you delete the A, then you delete the B. So however many letters you've got in your string, if you want to transform it into the empty string, then you would just delete those letters. That's why we put in the first row 0, 1, 2, 3, 4, 5, 6, 7, 8. The first column indicates how many edits are required to transform the empty string into some other string. If you've got to transform the empty string into the substring R, then the only way to do it is insert the R. So that's one edit. Likewise, if you want to transform the empty string into the substring RAB, then you've got to insert the R, you've got to insert the A, and you've got to insert the B. If you want to transform the empty string into any other string, the number of edits you need to perform is however many letters are in that string. Yeah, you just got to add them all one after another, or insert them all one after another, and you're good. So the first row and the first column are really easy. They're just counting. Okay, so that's the initial setup. That's fairly trivial, but things are about to get exciting. Now that we've filled in the first row and column, we can start the algorithm proper. So the meaning of the steps that we're just about to look at will really only become clear when we fill out the matrix a little bit more. So I'm just going to jump ahead just for a tick and half fill out the matrix. I've filled out the first 3 rows and about half of the 4th row, and we've got a little question mark just here. This box just here corresponds to the substrings CABBA and RAB. Yeah, so how many edits are required to transform the substring CABBA into the substring RAB? That's what this box signifies. But in order to figure this out, we've actually got the surrounding numbers in our matrix. So we've computed some of these values before, and we can use those numbers. This 4 just here, above the box that we're interested in, this 4 just here means that we've already worked out the edit distance between the substring CABBA and the substring RA is 4. This 2 just down here says that there's 2 edits are required to transform the substring CABB into the substring RAB. The other box that's interesting is this 3 just here. The 3 that's diagonally left and above our little question mark box, this corresponds to the substrings CABB and RA. Those 3 boxes just there are really what we're interested in when we're computing Levenshtein edit distance using the Wagner Fischer algorithm. What we've got is a choice from 3 different options. So we could take 4 edits to transform the string CABB into RA, and then we could insert an extra B on the end of RA and get RAB. The second option is we could say that it takes 2 edits to transform the string CABB into the string RAB. And then what we could do is just delete the extra A from the end of CABBA, and we'd have ourselves 3 edits. The other thing that we could do, it takes 3 edits from CABB to RA. We could substitute the final A on CABB for a B and get RAB. All 3 of those operations will produce the substring RAB from the substring CABBA. Yeah, we can delete, we can insert, or we can substitute. They're all going to produce that value. So what we do actually becomes really, really simple. If the 2 characters that we're comparing just here, which is this A and this B just here, if they're not the same, then we take the minimum of those 3 surrounding boxes, which correspond to the Levenshtein operations. We take the minimum and we add 1, and that becomes our next number. The other thing that can happen is if 2 characters are the same. So if 2 characters are exactly the same, then we don't have to perform deletion, insertion, or whatever. We don't have to do anything. And in that case, what we do, we take the box diagonally above and left, so this 1 just here, and we record that as our result. And the reason why we can do that is because if you look at it, this box that's diagonally left, what this indicates is the edit distance to substrings with 1 fewer character. Yeah, so this box just here says that the edit distance between the substrings CA and RA, the edit distance there was 1. If we add another character and it's exactly the same character, then the edit distance will be the same. We could just copy that 1 and put it there and we're done. So that's the 2 circumstances. If you start from our little matrix before, where we had just the first row and the first column filled in, just corresponding to the empty strings. So it probably seemed a little bit strange, but as you fill out this matrix, remember what you're doing. You're really computing the edit distance between a bunch of substrings, and you're recording it as you go, such that you don't have to compute it again. You can just reuse it again and again. It almost becomes so robotic and so simple. Yeah, you just take the minimum of those 3 surrounding boxes, or if the characters are the same, then you just record the same value that's diagonally adjacent. By the end of it, you've actually computed the edit distance of all of the substrings. Your final value in the lower right-hand corner is actually the Levenshtein edit distance itself. So drum roll, if you please, if you've got a drum handy or a roll. The edit distance between the words cabbages and rabbit is 5. I kid you not. One of the really interesting properties of this matrix just here, where you can actually build a list of the operations themselves. Okay, so let's talk about an optimized version, a much, much faster version than that. If you wanted to compute that matrix just there, what you might notice is that you only use 2 rows at a time. you need the previous row, and you also need the row that you're working on at the moment. We don't have to refer to any of these other rows ever again. And for that reason, there's actually an optimized version of the Wagner Fischer algorithm where we just use 2 rows of the matrix at a time. So that actually saves us RAM. And because you're using the same RAM over and over again, then it's actually better for caching as well. But things get slightly more interesting thanks to the brilliant code by someone called Mr. Martin Ettel on Rosetta Code. You can actually code this with 1 row and just a couple of extra variables. So the final version in the code, and I'll leave a link to the Rosetta Code, but if you think about it, when you're computing the Levenshtein to something, say this 2 just here, right? So CA, we're transforming the string CA into the string RAB. You really only need the previous row that you've computed, and you need the previous character. So this 3 just here. So there's actually a single row version of this Wagner Fischer algorithm, which I found to be the fastest. The trouble with computing this stuff with 2 rows and the 1 row version is that you no longer have the ability to build the list of operations like you did with the full matrix. As I said at the very start, we're talking about spell checkers in this little example just here. I'll leave a link to where I got my dictionary from. It's actually huge, and if you were writing a real spell checker, then you don't tend to use dictionaries with 200,000 words in them because they just end up suggesting a whole bunch of words that nobody cares about. But in my little test just here, I was kind of interested in the speed of the thing, so I got just the largest dictionary I could find. And I've just called it English 3 just here. I'll leave a link down below so that you can have a bit of a look at the same dictionary if you want. What we're doing here is I just load in that dictionary. Then we get the user to type a word. Yeah, we just read a word. And then I've got a priority queue. Yeah, a priority queue. So if you don't know what a priority queue is, maybe we could do a video on that at some point. They're interesting data structures. I don't know how many times this is going to go, but this is the original Levenshtein. It runs in about 30 minutes, so I don't think we can... For my testing, I just typed A a whole bunch of times. Yeah, if we just hit enter. It's hopeless. I mean, it's hopeless. Oh, it's trying to figure out how close A is to aardvark. And it's trying to figure out how close A is to varks and arcs and orcs. Okay, we don't need to time that. I might actually go up here and get rid of the bit where that Levenshtein types out something to the screen. Don't time things when you're C-outing because the C-out is going to take 40 years. This is the full matrix version. If we type a word, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I like to use the same word, just a string of A's, and we hit enter. So we can see that the time that was taking is about 124 milliseconds. The little spell checker there is checking the entire dictionary. It's looking for words similar to this misspelled word just here, 10 A's in a row. And the time that it was taking for the full matrix version is, well, I guess the smallest time is about 110, 111 milliseconds. Yeah, so it's pretty quick, really, considering the size of the dictionary. The string, 10 A's in a row, might be a Baka. Why is that in there twice? Oh, sorry, we're doing this 10 times. What a stupid, yeah, that's, it was repeating that 10 times. Yeah, if we actually want to compute the Levenshtein, we'll just do it once. Otherwise, it's going to keep adding them to the list over and over again. So these are the words here that it's suggested. These are the top 10 words, or the top closest matches to this string of 10 A's just here. Sarabaka, Malaya, Lamb, Adamantian. Yeah, and these are the distances that it's computed over here. So it takes 5 edits to transform the word 10 A's, or the string 10 A's, into Sarabaka. And the time that the full matrix version scored is about 113 milliseconds on my little machine just here. Okay, so the other way that we can do it is the Levenshtein row. Okay, so there we go. So the time for the single row version of Levenshtein, the optimized version, is about 48 milliseconds. So compared to 110 or 120 milliseconds from the full matrix version, you see that the single row version is much, much faster. And I assume, I've not looked into this a lot, but I assume that really has a lot to do with the caching. You'll see that the list of words and indeed the edit distances themselves are much the same. I don't know the running time of the original. It's something like n cubed or something like that. But the running time of these matrix versions is like n squared. And there's actually an interesting unsolved problem. It says, it's a conjecture, and it says that you can't compute Levenshtein any faster than n squared. So if you want a challenge, if you want a challenge, then have a bit of a look at that sort of thing. They call it, I think it's the strong polynomial hypothesis. I can't quite remember the name of it, but it's related to the P versus NP problem. Okay, so the final thing I might do is, instead of just typing ridiculous words, we'll see if it can actually suggest something for us. So it seems to be suggesting pretty good. Let's say that we want to transform. Let's say I'm trying to write the word dinosaur, but I misspell it. D-N-O-S-A-U-R-S. Dinosaurs. Let's see. There you go. One edit. Dinosaurs is the best suggestion there from our little spell checker. And the next is dinosaurs, or dinosaur itself. Yeah, it requires 2 edits. Yeah, so that's pretty much how spell checkers work. They just run through your little document, computing Levenshtein edit distances from all of the words in their predefined dictionary, storing those in a priority queue, then popping off the top 5 suggestions. That, my friends, is how spell checkers work. Have a good one, and thank you very much for watching.